Okay, today we're going to go over how to find whether a function is continuous at a certain point. So in the past, you may have been told that a function could be considered continuous over an interval or at a point if the curve of the function remains unbroken over that interval. Now that's a bit of a generalization, and it's best to come up with stricter terms. So that's what we're going to go through today. We're going to go through the three requirements that allow a function to be continuous at a point. So you'll notice that there are actually 4 bullet points up here. I'll go over that in a moment. But the first thing that's of importance to note is that f of c is defined. So meaning that f of c has an actual value and that f of c isn't undefined. So if f of c has a value, then it could be considered continuous. However, there are 2 other conditions. The limit as x approaches c of f of x exists. So what this means is that the limit as x approaches c from the left of f of x must equal the limit as x approaches c from the right of f of x. This is just a simpler way to state one of the conditions. Now, this is actually the definition of the limit as x approaches c of f of x. This can be described as the limit as x approaches c from the left of f of x and the limit as x approaches c from the right. So if these 2 are equal, then it meets another one of the requirements. And it's important to note that if a function at point C fails to meet any of these 3 requirements, then it can be considered discontinuous. So that's that. Now the final piece, the final condition is that the limit as x approaches c of f of x equals f of c. Now again, this right here, the limit as x approaches c of f of x, can be defined as these 2 right here in conjunction. So if these 2, if they meet at f of c, then it meets this final condition. Now, if a function were to fulfill all 3 conditions at point c, then again, it would be considered continuous. But if it fails to meet any of them, then it's discontinuous. And I've decided that rather than implementing practice problems for this video, for this topic, that rather I'm going to sort of ingrain background info into practice problems, if that makes any sense. Okay, so this is practice problem 1. I suppose technically it's part of the background info section as well, but I've decided that rather than introducing you to the name of the function first, or the type of discontinuity first, I'm rather just going to draw it and explain how it's discontinuous and then show you its name. So as a sort of way to show you how, as a sort of way to implement practice problems while actually giving you the background info. But the first discontinuity I want to go over looks something like this. You can see that it actually has no value at f of c. In fact, there's a hole at f of c, meaning that this is a discontinuous type of function because guess what? F of c doesn't exist, and therefore f of c isn't defined. So this right here is what's known as a removable discontinuity. Now, what's interesting about a removable discontinuity is that there are technically 2 types of removable discontinuities. And I'll show you the second. In fact, the second type of discontinuity is very similar to the first. However, it does have a value f of c. The issue with this value of f of c is that it isn't present where it should be. And I'll show you why. So one of the prerequisites of continuity at a point is that the limit as x approaches c of f of x is equal to f of c. Now, as I just said, this isn't found here because the limit as x approaches c of f of x should be this hole right here, what we could call pseudo f of c. However, f of c is not pseudo f of c. And if you're having trouble interpreting or visualizing what I mean by the limit as x approaches c of f of x, I'll just give you the second definition of this. So this right here can be rewritten as the limit as x approaches c from the left and the limit as x approaches c from the right of f of x. So again, this is just a good way to interpret the meaning of the limit as x approaches c. But if you'll I should have titled this graph f of x. I might as well do that now. What you'll notice as you approach c from the left is that we end up at the hole. And what you'll notice if we approach f of c from the right is that we again end up at this undefined value. Now again, since the limit as x approaches c, or rather the limit as x approaches c from the left and x approaches c from the right, it doesn't exist. It's not equal to f of c because f of c is up here. And therefore, this is another type of discontinuity. Technically, still a removable discontinuity somehow, but a removable discontinuity nonetheless. Okay, this is the second type of discontinuity we're going to go over. Let me draw you a representation of it right now. Okay, wow, that's terrible. Hold on. Okay, this is good enough. So this right here, hopefully you'll be able to immediately realize that this is indeed discontinuous, especially at point C, I suppose. Now, why is this? Well, first off, f of c isn't defined, so it already breaks the first requirement. Now, remember or try to recall that the limit as x approaches c of f of x can be interpreted as the limit as x approaches c from the left and the limit as x approaches c from the right. Now, the limit as x approaches c from the left is equal to infinity, and the limit as x approaches c from the right is equal to negative infinity. So these do not equal one another, and therefore f of c does not exist. Sorry, I don't know what I'm saying. Therefore, the limit as x approaches c of f of x doesn't exist. So this is already broken two requirements. So hopefully you can see that this is a not so continuous function. And this type of continuity is known as an infinite discontinuity. And it's quite identifiable. It's continuous at all other points except the point where the function diverges. Okay, this is the third and final discontinuity we're going to go over. Now, it's important to note that there are, I believe, technically two other discontinuities. One is both aren't seen in calculus AB or BC. The first is known as an oscillating discontinuity. The second, I don't believe actually has a name. In fact, it's quite rare, and I don't believe anyone watching this video will ever come across it. So the two types of discontinuities not featured in this video aren't to be stressed over, as it's impossible you'll see them in this AP curriculum. But let's go over the third and final one, what's known as, I might as well tell you now, a finite discontinuity. Now, finite discontinuities exist when the two values of a function, when the limit of a function, the limit as x approaches c of f of x doesn't exist. And that can be seen here. Now, not only does the limit as x approaches c of f of x not exist, but f of c itself isn't defined at this point. This point we'll call x equals c, per usual. So in this instance, f of c isn't defined, and the limit as x approaches c from the left does not equal the limit as x approaches c from the right. Now, what's interesting about this type of discontinuity, much like the removable discontinuity, it essentially has two types. Again, very similar, but slightly different. In this instance, f of c is defined. However, it's still known as a discontinuity because the limit as x approaches c from the left, again, doesn't equal the limit as x approaches c from the right. So those are all three of the types of discontinuities seen in calculus A, B, and BC. Again, it's unlikely you'll ever really need to use these. I mean, they occasionally come up in AP exam tests, but very few questions actually revolve around limits, despite calculus being all about limits. So that's it for today's video. I'll post videos on the future about limits if anyone's curious about them. However, in the meantime, please try to make a comment suggesting what I should do for future videos. Thank you.